So let me just summarize what I think I heard today. So Trevor Mudge said that we do not really understand mobile phone workloads. Bengt, Werner said that we do not really understand parallelism bugs in applications, therefore we need deterministic simulation. David Black-Schaffer and Trevor Carlson said that we do not really understand performance of these things, and we need faster simulation techniques to figure that out. Christos Kozyrakis said that we do not really understand data center workloads. I'm joking, of course. We had fantastic insights in all of these things. And Bernd said that if you go to 1 million threads, then you really need to visualize what the system is doing to get an insight. Of course, we heard fantastic insights in all of this, and of course I'm joking about this. But the real question is that we were sort of forced into the multicore era by failing to continue frequency scaling, essentially, right? So when the companies were unable to continue down that path, they started developing more and more cores. So the question is that, was that too premature? Was software, is it just that software takes a long time to adjust to changes in architecture? What did we do right? What did we do wrong, right? So that's the kind of questions that I ask the reviews on. And to be honest, this thing happened from the dawn of time, right? So we built the first computer, we ran the first programs, and we observed, oh, there's locality in the programs, right? So we built caches, and so on and so forth. So there was always this cycle of building hardware, then trying to understand what the programs running on this hardware do, and then improving both on the software and on the hardware. But the feeling I get today, and correct me if I'm wrong, is that this is almost at the point where it's getting out of hand with all the new workloads that are coming, workloads that we never had before, mobile, data center. We, of course, had the HPC workloads, but never at that scale. So is this getting out of hand? How do we go forward? So let's start. So you see the chefs up there. So Trevor is the first to go. So Trevor, what do you think?
Well, you pointed out that everybody's raising questions and basically got a pessimistic view. You know, there's problems everywhere. And I think that that's really a consequence of the fact that we want to keep ourselves employed, basically. And so without problems, why do we need researchers? So, but more seriously, I mean, the parallel processing thing is a problem in general. I mean, there's special cases where you could do lots, but it's been around for a long while, since I was in graduate school, which is a long while. And I worked on ELIAC 4, if anybody remembers. That was a very early parallel machine. And we haven't made a lot of progress, but we've only been doing it for 50 years. I mean, physicists and chemists have been doing that thing for, several hundred. So I don't think it's going to get solved overnight. That's the half-full version. We'll get it done in another 100 years.
You're saying Nobel.
Yeah, exactly.
So the second chef up there is Christos, I think.
Okay. All right. So I think that's a good point that you made. And maybe the one issue that we need to finally address is the following. So we keep going back and forth, change the hardware, change the software, change the hardware, change the software. And most of the times, the changes that we make in hardware we eventually convince Intel or Intel convince itself to build them, and it's fine. And then there's nothing else to buy, and you buy them. But in the hardware, in the software side, it doesn't happen as fast. I think the problem is that we still don't have really good abstractions to talk about anything other than functionality. So, for example, in many things in the data center side, you try to basically say, tell me the most resource-efficient way of getting something done. How do you understand resource usage at the software level, if you have no clue how the hardware works. And we tend to forget this. For example, like, even in more conventional systems, we think about caches. Most programs have no clue what caches are, how caches work, and then we expect them to write good software for them. So maybe what we're missing is a few things that are providing the framework to communicate between the hardware and software, so it doesn't have to be heroic research efforts every single time to get one new operating system, one new debugging tool, and one new simulation tool every time that we do them and do these things right. There are some people working on that, like Jim Demel at Berkeley, who's working mostly on trying to rethink algorithms so that you model most of the memory behavior rather than the compute behavior, if that's the bottleneck these days. So maybe that's the thing that we haven't done that much work with the abstraction level.
Is that a language level, at the language level, or?
It's a good question, I don't know. I think that eventually get codified in languages, but I don't know where this needs to start from. So we did such a good way of telling people that, write whatever you want, you're going to run it fast, that now we don't have any way of telling, help me a little bit run it fast, give me some information which is not that much system specific to the specific supercomputer you have today compared to the one you get in 6 months.
Bernd, what do you think?
Okay, there's two things. I agree with Trevor saying that stuff is around for a long time, but no one had a good idea, and this shows how complex the system is. But one aspect of it is that computer technology develops extremely fast. Yeah, so basically we have new systems, new paradigms coming out every few years, and like the physicists and chemistry people have it easier. Like the world is out there, and they can test on their theories for years, while when I'm working on something after 4, 5, 6 years, my whole context have changed, and I'm running behind all of that. A second portion, which I think might be a source of a problem, is how we train programmers. Because we know from the beginning, everything is parallel. Yeah? Even if I say, okay, I have a single process computer, but I still interact with servers and so on, this is happening distributed in parallel. And now, of course, with the multicores and so on, but we still teach people mostly sequential programming because this is what we understand and can tell about. And then we get them into a head, how to get one step after the other, and then they come to the work or things, and then suddenly, oh no, it's parallel, and you somehow have to put it on top of it or something. So I think we would need to start teaching people thinking in parallel from the beginning, and hopefully then we raise a generation which are more natural to thinking in parallel? I don't know.
I think the students already have picked up on that. So, for example, I have now a project where the students decided to do the project using Go. Rob Pike developed that at Google. So this is a language that allows you, allows you to do TCP connections and all these things really easy, right? So you can do servers and clients.
I agree, it's changing, yeah? So now we have threaded building
right?
in C++ and Java and so on, but it's still, so people still learn about searching and so on, but we should like more scheduling and, I don't know.
What kind of parallelism? Are you talking about
both
parallel algorithms or distributed systems? Because they're slightly different, I would say.
I think both is important, yeah, and so both needs to be taught.
So first of all, we should give ourselves a little bit of credit. Okay, so as Trevor said that it's problems, but we're still doing an amazing job. How many other fields of engineering do you know that they're scaling at exponential rates? Go to your civil engineering friends and ask them, what would you do if cement or steel was improving in cost and efficiency exponentially?
Up to 2004.
No, we still, we do it in a slower pace, but we're still scaling exponentially. It's not the end of the world yet.
I agree. I'm playing devil's advocate.
We are not civil engineering yet.
Yet. Okay. So, Bengt, what do you think?
So, I think we need to learn that computer systems are so complex that from the start you should think about how to instrument them. They're not built just to serve its purpose. They also have to communicate back what they do. And I think that's really in its infancy. So building simulators, we've had to use the little instrumentation which is put into processors, multicore processors. And it doesn't work. It's put in there, but it's buggy. So even those simple things which have been put in there are not correct. So I think we can do lots more. I mean, we heard previously in the talk about sort of the big data systems, that there are a lot of things more we need to measure. It's not only simple instruction counter or debug breakpoint. There's all these power things we want to measure everywhere in the system, not only in sort of the central parts of the core, but everywhere. So I think that is something when you design systems, you should think much more about from the start.
Okay, so you think more emphasis should be put in feedback from the hardware itself on how the software is doing.
Oh yeah.
But that would lead to the improvement of software or next generation hardware or both?
I don't know. Lots of the things we're doing here is partly a little bit workaround because the machines can't tell us the answers about what's going on, right? So then we have to invent simulators and all these nice techniques to try and figure out what's going on.
David?
So I agree with Christos here in the sense that we've done a phenomenal job. And I think we need to be a little bit realistic about this. I think we've gotten 50% of the parallelism that's reasonably out there. And it's all the easy parallelism. It's data parallelism. You know, it's the OpenMP parallel for the multiple independent programs running together. And we've gotten that with remarkably little effort. I mean, for that sort of stuff, we've managed to train people and get there and do a good job with it. I'm less optimistic about the remaining 50%. I think it's going to require a huge amount of work, both in education and in terms of instrumentation and tools to get there. And I think that that's a real challenge. We need to think also about how much that last half is worth. And the reason I say that is because if you look at the other things we can do with parallelism, I think there may be more promising avenues there. So one that I'm particularly interested in is if you look at what's happened with JavaScript. Inherently serial, horrible language, it's incredibly slow. And so people say, I've got all these multiple processors, so I'll use those other processors to JIT my JavaScript and optimize it. So not executing a parallel problem, trying to use all these extra resources to speed up whatever problem we have around. And I think that sort of assisted approach may be a better use of these parallel resources than saying we've got to write our code inherently as parallel as possible from the beginning. And I think that we're going to plateau at the level of education we can expect from our developers. How much parallelism can they really expect? I think we're going to plateau at the level of how much can we really instrument and infer from the instrumentation what sort of parallelism we need. And I think we need to think carefully about how to use these resources because they'll be there if it's not cost effective to go beyond that level.
Why do you think the difficult parallelism is 50%? I'd say it's 5%, 1%.
I think maybe it's not the absolute number. If you look at sort of the cost-benefit curve, I think we were already way up on the part where it's getting very expensive to get more benefit. And maybe we've only gotten 5%, but that cost is not low.
So the way I think about it is, let's suppose that we get to 1 million cores. So some people are already in the 1 million cores. There are two ways to keep 1 billion cores basic. It's either you write a loop that says for every request or for every I and so on, or you have to write 1 million different thread functions. Nobody will do that. So the only parallelism that will scale is the easy one. Of some kind, requests, pixels, I don't know what else.
Yeah, and we've done a fantastic job of getting that. And I'm just saying that there's a very steep cost for getting up on that curve, and that we need to think carefully about it.
So it's all done, I guess.
On that, I would like to...
Or we should do other things with it, potentially.
To take on...
You mean build bad programs so that we can use the other cores?
Well, partially. But if you look at it, what we've done with things like JavaScript, PHP, and Ruby, we've built horrible programs which allow massive numbers of developers to build new stuff. And so we've, not intentionally, but we've explicitly traded off horrible computer software for ease of access.
There's something about that logic that doesn't make a lot of sense. I mean,
that's where we are.
We could keep building really bad code or whatever and use, the extra cores to improve it.
And that's what we've done, and that's where this exponential growth has come from.
That's for sure.
Trevor,
But can't we blame the hardware architects for a change?
Yeah.
I mean, why do we have this horrible complex software? Because with hardware, basically, we're throwing up like, oh yeah, here, like, I give you free level of cache, and I change the policies all the time.
We just have terrible processors.
They should design a processor which is easier to use.
So the question
if we only design processors which are harder to use.
Yeah, that's right. Put crappy software on them, and then we'll be
I think I've got the solution for you.
So yeah, the general question is, do we understand what the programmers want? How they want to program, right? They want to use JavaScript. They want to use
I think we do.
Futures in C++,
we do. The
right?
problem is there's millions of them, and they all have different ideas what they want. Yeah, the application space is so different and the requirements that it's hard to say. I mean, this is why a lot of people say, okay, yeah, like Anton machine or something. So I want to do my molecular dynamics as fast as possible. I write a machine which just can do my thing and so on. But in a general purpose data center or general purpose computing center, it's hard because, I mean, people can apply in Germany for compute time, and I don't even know, like, which applications would need to run on my machine in 2 years. So.
Okay, we don't have to accelerate everything. Let's look. People are reasonable to some extent. Like they try to optimize for metrics that the value. So look at what's happening in data center. You have a startup. You know they want to run some new service. Initially, they have 20 machines. That's not what they need. Okay, and those 20 machines are not expensive to buy, but hiring the 3 system administrators and 20 programmers to program them is really, really expensive for them. So they go to Amazon, they rent the machines, and they use the Amazon APIs. So they may be running crappy JavaScript hardware, software, but they couldn't care less because they scale out and it's fine, and they can afford it, and it's not worth touching that software and making it better. Some of them eventually graduate to become companies with 1,000 machines and many engineers, and then the bill looks high, and then they're motivated to go and optimize it using the wonderful tools that we produce, hopefully. But yeah, that initial Ruby code, JavaScript code, let it run. The way that Amazon deals with this problem, because like 1 million people give them the crappy Ruby code, is that they say, don't run Ruby as it is. I'll give you a higher level API, Elastic MapReduce, whatever, container service, this and that. Use my better service, higher level API, and program to that, and that's how those programs get to disappear. So we don't have to worry about getting every program to be fast and every language to be good, okay? Just provide alternatives, and people who actually value it will switch to that. The rest, they'll suffer, or it may not matter to them. It's fine.
Yeah, I'd like to take on Trevor's talk on the issue of the easy parallelism versus. So you said, you claimed that we need 2 ARM cores, right? General purpose, but they call them ARM.
No,
but
I don't claim. I just said that if you look at the evidence, there's not much reason to put more general purpose cores in a mobile handset. That's all.
Okay, but 2 cores and 64 kilobytes.
No,
fine, but and also a GPU next to it, right? Because and a GPU.
Many GPUs, actually.
Many GPUs, right?
What was
because
before in that?
Angry Birds may need 1.2 general purpose cores.
I'm not saying there isn't.
It drives a 2 million pixel display, right?
I'm just telling you what I observed. And what I've observed for the last 20 years is that in this particular space, there's not been much progress in parallelism. That's all.
I disagree here.
Well, I measured it. I mean...
No, the thing is, when you say the apps you measured are not using the parallelism in your general purpose core, I agree. Yeah, but the games are using the GPUs. Each of the softwares are using the camera sensor, the video sensor, and so on. And so these people have to basically make sure they're using all these different units. And I mean, I don't. For me, that's parallel. So I'm using different execution components to work together.
This is exactly what Christos was saying. They've got an API, the graphics API, which does all the parallelism for them. They haven't written any parallelism when they do that. They wrote a single serial shader, and then the API just did it in parallel.
And wait for it and so on. So there's some parallelism
but
involved.
Very, very little compared to what it gets because they have
better ways to exploit the easy parallelism, and it's fine.
Yeah.
That's right.
So Christos, is that the way to go for data centers? That is, right, not GPUs, accelerators, right? The Microsoft way. So Microsoft takes the way of, we're not going to have a huge number of servers, we're going to have a much smaller number of servers, but very a lot more powerful accelerators with each one. So you claim 10% for the cost of the accelerator, right? That's okay. And no, $10 or whatever.
10 watts or
10
no
watts,
power.
10, fine, 10 something, right? But not 200, right?
So maybe the 200 can work as well. The problem is that the moment you come up with the 200 one, they have to replace a CPU with it. They cannot put it next to a CPU. So it's a trade-off, like how often is it used? But the 10 watt, they can just deploy it almost easily.
Okay, so I think it's about time to close.
Any questions from the audience?
I think we have. Yeah. Let's thank the speakers. Thank you very much. And thank you all for coming, attending this day. So we are endeavoring.